Hi folks, this is going to be the subject of this video. It's a directional gyro or a heading indicator. It's air powered. You can see on the back here, I'm sure if you can see it, let's put a light on it. At the top you've got the vacuum port, so you could power this using a vacuum pump. You've got cage there. I'm guessing you take the bung out and insert something to keep it caged whilst you test it, something like that I guess. And then you've got the air inlet, which is the one I'm going to be using. So I'm going to be putting pressurised air into this thing. And it just so happened that this standard fitting off a compressor hose fitted the threads perfectly, so that was very convenient. If I turn it around to this side, it tells us not to exceed 20 inch-pounds of torque, so I know what pressure to apply, or not to exceed anyway. And you can see it's still got these warranty seals on just here. It's manufactured by BF Goodrich Aerospace. You can see here it's got the cage knob, so this is what we would use to set in the heading, aligned to the magnetic compass. And it just so happens that it has a nice scale on here, so we can try and capture some apparent drift, because these things, according to mainstream science, absolutely record apparent drift and must be corrected because of it. So I'm going to be testing this in this video later on, and we're going to see if it actually does indicate apparent drift, or whether it only indicates mechanical drift due to friction in the bearings.
Okay, let's go back and have a brief look at how it came to be that gyroscopes are supposed to be able to record or demonstrate the rotation of the Earth. So according to Wikipedia, this man here, Leon Foucault, in the mid-1800s invented the Foucault pendulum, which was suspended from the ceilings of very tall buildings throughout Europe to demonstrate the spin of the Earth underneath them over a prolonged period of time. In 1852, a couple of years later, Leon Foucault came out with, quote, conceptually simpler experimental proof of the spin of the Earth using a gyroscope. So I found a paper online, which I'll provide a link to in the description, written by somebody at the Université de Rennes in France. So it says, Foucault gyroscope and induction current apparatus in the University of Rennes physics collection. So it's written by these two guys here, which I'm presuming is these two. So this paper talks about two instruments. I'm not so bothered about the induction current apparatus. So let's read on. The French physicist Leon Foucault is best remembered for his 1851 pendulum experiment. The slow clockwise veering of the swing plane reflected the anti-clockwise rotation of the Earth beneath, and finally provided the first dynamical proof of the terrestrial rotation. And here's sort of a diagram of it. So the following year, in 1852, Foucault devised a new experiment for demonstrating the Earth's rotation. He called it the gyroscope, from the Greek words meaning to look at the rotation. So low friction gimbals allow the spin axis of the torus to stay fixed in space. The microscope or pointer are used to monitor the slow drift of the axis relative to an earthbound experimenter. And this apparatus, using the crank handle to spin the torus up to 150 to 200 revs per second before it is placed in the gimbals, which is here. So the pendulum veering rate includes a sine latitude term, which I'll be using later. The gyroscope follows the stars directly and was invented by Foucault to provide conceptually simpler demonstration of the Earth's rotation. So the University of Rennes holds a Foucault gyroscope set in its physics collection. The set was acquired in 1875, probably at a cost of 1,500 francs, which is $300. The maker is the firm of Dumoulin-Froment, successor to the Froment firm that made Foucault's original gyroscope in 1852. So note, this is not the original gyroscope. And whilst we're on this slide, let's just look at the size of the guy's hand in comparison to the gyroscope flywheel there. I first thought that the gyroscope was much bigger, but when you actually see it with a reference, as in this guy's hand, you can see how small it actually is. And here is the apparatus that's used to spin it up. So Foucault gyroscopes are exceedingly rare, perhaps because they were very expensive, 1,500 to 2,500 francs. So not for the common man. The original 1852 gyroscope was bequeathed to the Collège de France and has been lost. Really careless. We know of only 3.5 other sets besides the Rennes one. And they are, there's one in Paris in the Musée des Arts et Métiers. There's one that this one's talking about in Rennes. One in London, Science Museum, Coimbra, and the Washington Smithsonian Institute. If you know of other Foucault gyroscopes, please let us know. So a gyroscope set came with 2 rotors. One is missing from the Rennes set, the other has broken suspension pins, so we have not yet been able to set the gyroscope going. What? Not yet? According to this, you've had it in your possession since 1875. So 144 years later, and they've not yet been able to set the gyroscope going. I guess we can't fabricate some pins in this day and age. We just don't have the technology anymore. However, various accessories have survived that could be used for demonstrating other properties of rotary motion. And there's a few more pictures here, and then it goes on to the induction apparatus, which I'm not really interested in. So let's go on to have a look at some pictures of this original apparatus. So this one here, this would be used to first balance the gyroscope so that there was no sort of bias on the weighting either side. Then it was obviously put into this apparatus to spin up. Once it was up to speed, it was then taken out and put in here, and the long pointing arm here would record the rotation as the Earth spins, and this remains rigid. The microscope here was used to view some small graduations on the side of this outer gimbal here. It's just a second way to observe this supposed rotation. There's just a close-up of the balancing instrument, and a close-up of the instrument that's used to spin it up. And here's a close-up. I'm going to zoom into here and just show the top. So there's a little hook here onto which a low torsion cord would be suspended down. This is obviously threaded, so you could screw this up and down by hand. The cord would attach onto this little loop, and the whole gimbal here is able to spin freely upon this domed piece of steel via this tapered conical piece of steel to form a low friction bearing point just here. The sides of the gyroscope here, these bearings are called knife edge bearings. I'll show you a close-up of them in a second. And obviously the bearings in here and in here that are the main spin axis bearings, they weren't even ball bearings, because ball bearings hadn't actually been invented. They'd been patented already, but not manufactured by 1852. I think it was 1869 before the first ball bearings were actually used. So much more inferior bearings in here than what we use today. And here are the close-up views of the knife edges just here. Obviously this would be placed in here so that the spin axis was horizontal. Okay, so I have replicated this setup, and the next few experiments are going to be demonstrating what I have come to learn from them.
Okay, so this is a brass gimbal set that I purchased. I've taken it apart. What it used to look like is this, and what it's for is you attach the bracket to the wall of a boat or a yacht, and you place a liquid fuel lantern through the central gimbal, and then no matter which way the ship rolls or pitches, the lantern stays vertical, stays upright all the time. So I've purchased this, took it apart, and this is going to form the gimbal set, or the gimbal mounting for my new gyro experiment. So I don't need this central part, that will be discarded, and it will be replaced by the gyroscope. So for the low friction sort of bottom pivot point, I'm going to be using one of these, which is a speaker spike. You have 4 of these and you attach them to the bottom of a speaker, and the idea is that because only a tiny little bit of the surface is making contact, it prevents resonance and loss of sound. That's the idea anyway. But I've bought this and I'm going to use it as the bottom part, so this will sit through here once I've threaded it properly. I might have to cut a bit off the top, shorten it down a bit, but essentially that's going to be the part that contacts with this part here. It's called a low friction pivot point. Okay folks, this is the assembled experiment. So I've used a lab stand, and I've modified it by drilling 3 holes into which I've inserted some adjustable feet so I can level the thing, and you can see that it's nice and level. I've also drilled another hole into which I've fixed a bolt, which you can just see sticking up there. Obviously that's height adjustable as well, and above it we can see this gimbal, and you can see the speaker spike inserted into it. It's suspended via these 2 lifting eyes and a piece of cotton, just 1 strand. Probably not the best idea putting a piece of red cotton on this red background, but I'll just spin around here so you can see it. And I'm able to use this hex key adjustment here and higher and lower this gimbal, and I can lower it so that the speaker spike drops down nice and gently and controlled onto the bolt. So as you can see, if I go to the end here, the little piece of metal you can see there is part of a pencil sharpener blade. I've just cut it in half, put 1 on each side. So these, I guess, knife edge bearings here, they're not quite a knife shape, but the diameter, I would guess, is not far off the bottom of the knife on Foucault's knife edges. And you can see I've perfectly balanced it using the weight that comes with the gyroscope on this side, and I've hot glued a bolt on the end and some washers, and I've just kept adding washers until I got it perfectly balanced with this socket that I've managed to fix onto the other side. It's a bit crude because I'd use these big long bolts that you can just see just there, look, but they're not impeding anything, so they're all good. But this thing is absolutely perfectly balanced now. I'll give you a quick demonstration. Obviously knocked it a bit so it's wobbling. As you can see, it's keeping sort of rocking back and forth. And it will do that until it finds its level.
Still moving. And you'll note that the whole gimbal is continually spinning. And it'll spin this way for a time, and then it'll stop and start swinging back the other way. And then it'll stop and start swinging the other way again. It will eventually find its own resting point, but it takes a very, very, very long time. And it's very important to note this, because I've discovered something with gyroscopes that I didn't really know before. I've not seen demonstrated on any gyro video. I've seen Eric Laithwaite's video series on gyroscopes, and there's the other professor, I forget his name, does quite a lot of gyroscope experiments and demonstrations, but I've never seen what I'm about to show you demonstrated before. And it appears that a gyroscope loses its rigidity in space property when suspended like this. So I'm going to spin it up and show you what I mean. It's quite bizarre, and I didn't know that this phenomenon actually occurred with gyroscopes. So I'm going to stop the video now and get it spinning. Okay, so I'm going to be spinning the gyro with my Dremel tool, and you can see there it's 33,000 RPM. That's no load, but it will virtually be no load once it's up to speed. Let's spin it up then. So let's observe what happens. Can you see what's happening yet? It's rotating clockwise. Really, really quickly. And it will continue to get quicker and quicker as the speed of the flywheel slows down. But you'll notice that in this direction, no movement whatsoever. It's not processing. It's like it's lost its ability to remain rigid in space. And just to prove that it is still working as it should, as a gyroscope does, let's impede the movement. You see what's happened? It stopped, and it's now spinning anti-clockwise. And there was a very, very slight bit of precession that occurred when the gimbal hit the little crocodile clip there, and it tilted it very, very slightly. Let's see if it's going fast enough to do it again. Now watch carefully, watch this axis very carefully to see if it moves when this touches. Did you see that? Precessed itself back up straight again, and it's sending it back round clockwise now. It will continue to do this, and it will actually in fact carry on going one way and then stopping and coming back the other way without me impeding it. But you can clearly see it's moved quite a long way from the crocodile clip there now. And to further prove that it is still working as a gyroscope should work, I'm going to move it manually. Put it back straight again. Let's see what it will do this time. So it's going quite fast there. But still none of this going on. It appears that the fact that it is suspended and that the thing is able to spin freely makes it so that this thing will continually turn. So there's still plenty of momentum in this flywheel. It's still pretty difficult for me to turn like this. In fact, it's stopping me, look. It would rather precess than let me turn it. A lot of resistance. Still loads and loads of power left in this flywheel. So anyway, next experiment, I'm going to lower it down and get it to rest on top of this bolt. Okay, so I'm going to lower this down now by turning this hex bolt and holding onto this little eye, and it'll lower this whole thing down. So let's just have a look at that. very, very slightly resting. Not quite in the centre, but let's see what happens now. It's really going fast. No rigidity in space whatsoever. Okay, let's try impeding it again. Bit of precession. I'm now going the opposite way. And again, to test, to show that it's behaving as it should, obviously it wants to work its way off. I'm having to do it very gently. Okay, so this time I've let it come to a complete rest, and I've added a protractor and a paper clip as a marker, and we're on 129-ish at the minute. So I'm just going to give it a quick nudge and see if we can get it to come back to its original position. There we go. It's 128 now, it's close enough. Just spin it up. Okay, you'll note I haven't got it quite straight. It's slightly over to the right at the top. But let's just observe what happens here to this angle. Anyone guess what's going to happen? Okay folks, I think we've given that enough time. It's not moving. There's still energy left in this flywheel though. So let's give it a little push.
Okay, so we saw how by letting it come to a complete stop before spinning it up, it would appear not to show any apparent drift whatsoever in either direction. I've done it countless times now. I've got lots of different experiments on video in all different scenarios. I did it lots and lots of times, and not once did I see anything that resembles apparent drift either in speed or direction. We also saw earlier how a particular rotation or direction of rotation can be induced into the gyroscope. So it doesn't take too much of a stretch of the imagination to wonder if the rate at which it rotates could be controlled. And I'm just putting this out there for consideration. I'm not saying this is what it was for, but let's just take a look at the top of Foucault's gyroscope here and look at what the function of this could be. It looks like to me it puts a pressure on the pin there, and it looks like it's threaded. So you could fine-tune that if so desired to slow the rotation down to a certain speed given a bit of trial and error. I mean, I can't think of a logical reason why you would need this. I certainly didn't need anything like this in my experiment. The only other thing to consider, I suppose, is that this isn't actually the original gyroscope from the original Leon Foucault experiments. That one was lost. So I guess we'll never know what the actual one looked like. We can only presume that it looked similar to these ones. Anyway, that's the end of part one. I'm now going to move on to the aircraft instrumentation section to this. So I've watched this Navy training video countless times now to really try and get it into my head, everything that he's saying. So I'm going to play certain parts of it now, and I'm going to be commenting on certain parts of it and analysing certain parts of it, just to put you in the picture as to where I am at with the whole gyroscope thing.
Modern high-performance aircraft require electric gyroscopic instruments. The turn and slip indicator, the attitude indicator, and the directional gyro. This film will explain the theory of operation of some of the newer electric gyroscopic instruments. To understand any gyroscopic instrument, you must understand the principle of the gyroscope. It consists of a rotor mounted in a gimbal. The rotor can spin in one plane only. When another gimbal is added, a second plane of movement is possible. And when this assembly is mounted in bearings, the rotor has 3 planes of movement and can assume any possible attitude. This is now a freely mounted gyroscope. A spinning gyro has 2 important properties: precession and rigidity in space. All of its practical applications are based on these 2 properties. As for rigidity in space, the spinning rotor remains in its original attitude, while the gimbals and base move around it. In other words, the gyro maintains its axis in relation to space and not to the surface of the Earth. If a gyro moves around the Earth, its axis is vertical to the Earth's surface here, at an angle here, and horizontal here.
So very clearly here, he is saying that a moving object, like an aircraft, that is moving along the curvature of the Earth, because they are actually tilting as they move in relation to space, then the gyroscope will remain rigid and won't move. So it will appear to an observer in the aircraft that the gyro has actually moved. So that is clearly what is being stated here.
The gyro will resist any force that attempts to change its plane of rotation. This leads to the principle of precession. When a downward force is applied here, the gyro moves, but not in the direction of the applied force. Instead, it moves at right angles to the applied force. This action is known as precession. If an upward force is applied at the same place, the gyro again precesses at right angles, but in the opposite direction. The explanation is simple. The rotor is spinning in this direction. When the force is applied, the gyro precesses in the direction to align the direction of rotation with the direction of the applied force. The rate of precession is in direct proportion to the applied force. Small force, slow precession. Greater force, faster precession. If enough force is applied, the gyro precesses a full 90 degrees. However, at or near 90 degrees, it will tumble and go out of control. This disadvantage must be overcome in gyro instruments. Another disadvantage comes from the gyro's tendency to drift away from its original attitude. There are two types of drift. One is mechanical, due to friction in the bearings. The other type, known as apparent drift, relates to rigidity in space. Once again, consider this condition. The gyro maintains its attitude while the Earth turns under it. Every 6 hours, the gyro drifts through 90 degrees in relation to the Earth's surface.
Okay, I've got to stop it there because this is where a lot of confusion arises. So you can clearly see by the video here that he is talking about gyros located at the equator. You can see Antarctica there. So those gyroscopes are located along the equator. And you'll also note that it is a vertical gyroscope, at least in its starting position. It has to be vertical and it has to be on the equator for the 90 degrees in 6 hours to occur. If it's at any other latitude, then a different amount of apparent drift is said to occur.
In order for the gyro instrument to be dependable, drift must be corrected continuously. There are several types of erection systems that correct for drift. The principle back of all these systems is based on 3 steps. The direction and degree of drift are measured by electrical or mechanical sensing elements. These elements then control the application of a proper force to the gyro, and it precesses back to its normal attitude.
So he does go into quite a lot of detail on how these actually work, using servo motors and the sensing elements to send an applied voltage to the motors to precess it back into its original position. So feel free to watch that video in its entirety, but I'm going to move on from there.
All gyros in this film are actually the rotors of electric motors. However, for simplicity, we will represent them like this, and this.
Okay, so I've drawn the missing axes on each of these gyroscopic instruments. We'll start with the one on the left, the turn and slip indicator. This is probably the simplest of the 3. It uses a spring to return itself back to centre each time once the turn is finished. So I'm going to disregard that particular one. The artificial horizon, or the attitude indicator in the centre there, is the one we've just been looking at, and this is the only one of the three that remains rigid, as in it stays in its original position throughout an entire flight. So the whole gimbal housing, or the instrument housing, rotates around it as the rotor stays upright. And since we know that mechanical drift occurs, there has to be some mechanism by which these gyroscopes erect themselves continually, because it is bad practice to set them during flight. You have to set them before a flight to a known straight and level reference point, i.e. the ground. That's the whole point of them. The last one there on the right is the one I've got, and you can see I've drawn the vertical missing axes here, so the whole thing is able to spin around that axis. And as you'll see, there's no means for gravity to work on this one to assist it, to bring it back to center, since it spins on that vertical axis. And since the gyroscope I have is air driven, it has no means for any external device to be plugged in to correct anything. It just hasn't got that facility. So before we move on to the directional gyro, I'm just going to play a short clip from another video that explains how air-powered artificial horizons or attitude indicators, i.e. the one in the center there, works, because I believe there's a good test we can do to determine whether the pendulous vanes on these instruments, which is the method by which they remain erect, actually do correct for the rotation of the Earth, or whether they are just correcting for mechanical drift. So I'm going to play this video and they'll explain how it works, and then I'll tell you my idea of how, if I'm able to attain one of these air-driven artificial horizons, I can test it.
The Earth gyro in the artificial horizon or attitude indicator may be air-driven or electrically driven. Let's look at the air-driven version first. In the air-driven artificial horizon, the spin axis of the Earth gyro is tied to the Earth vertical by a system of pendulous vanes and air jets. Any tendency for the gyro to topple is counteracted by the precessed reactive force from the air jets. The centre of gravity of the gyro is also kept below its pivot point on the inner gimbal to assist in keeping the gyro vertical when not in use. Let's look at how it works in more detail. If we look at a diagrammatic view of the gyro and rotor housing, we can see that at the base of the rotor housing there are 4 air exhaust ports. Each port is partially covered by a pendulous vane, which we will call A, B, C, and D. Air is exhausted through the partially open ports, and when the gyro rotor is vertical, the air being exhausted through the ports will be of equal and opposite pressure. However, should the gyro rotor axis wander from the vertical, the pendulous vanes on opposing sides of the rotor housing move, so that as one vane closes, the other one fully opens. In our illustration here, the gyro rotor is toppling, and we can see that by gravity vane B has closed, while vane D has fully opened. The result is that the air pressure escaping through the opposing port D will no longer be balanced, and the excess reactive force is precessed through 90 degrees in the direction of rotation of the rotor to re-erect the gyro.
Okay, so now we know what the pendulous vanes are and how they work. We also know that the pendulous vanes in the air-driven artificial horizon are the one and only means to compensate for apparent drift, i.e. rotation of the Earth. So it seems to me that if I was able to get hold of one of these things, open it up and disable the pendulous vanes or remove them completely, then test it, it should bring apparent drift right back and should start demonstrating it. I'd like to know what you guys think about that, or if anybody else wishes to buy one of these gyros and test it for themselves and make a video, then please do so, because I'm going to continue with the directional gyroscope for the rest of this video, and we're going to leave the artificial horizon behind.
The aircraft heading is indicated here, and the reciprocal heading here. To obtain this information, the instrument uses a freely mounted gyro. Due to its property of rigidity, the spin axis of the gyro will hold its attitude as the aircraft and instrument case turn about it. Secured to the outer gimbal is a gear. Its teeth mesh with the teeth of another gear, to which the compass card is attached. Before it can indicate correct headings, the compass card must be set to the heading of the aircraft, as indicated by the magnetic compass. The push-to-cage knob is used to make the setting, after which the gyro controls the compass card. Assume the aircraft makes a 90-degree turn. The instrument case turns around the gyro and lower gear. As a result, the vertical gear makes a quarter turn as it travels around the lower gear. So the compass card also makes a 90-degree turn. In this instrument, apparent drift causes the compass card to drift away from its heading about 3 degrees every 15 minutes. In this instrument, apparent drift causes the compass card to drift away from its heading about 3 degrees every 15 minutes. In this instrument, apparent drift causes the compass card to drift away from its heading about 3 degrees every 15 minutes. And so, every 15 minutes, it must be reset to the magnetic compass heading.
So this 3 degrees of drift every 15 minutes seems to be a universal doctrine taught to all pilots worldwide since at least 1960, when this video was made. The thing is, the pilot is never taught to be mindful of which direction the drift will occur in. You see, if apparent drift caused by the rotation of the Earth was actually happening, the drift, or the direction of the drift, would undoubtedly manifest as a definite bias in one direction depending on which hemisphere you're in. Mechanical drift caused by friction in the bearings is a cumulative phenomenon and occurs as a result of constant attitude adjustments in an aircraft. If an aircraft flies straight and level and makes no adjustments at all, then no mechanical drift can occur, since there is no movement in the gimbal bearings and therefore no friction is generated. From personal experience, witnessing the directional gyro drift in both directions during the same flight in the same hemisphere, I can say with absolute certainty that there is no bias in any one direction, which would absolutely be necessary if gyroscopes were remaining rigid in space with the Earth spinning under them. Furthermore, pilots operating around or near the equator should have experienced no apparent drift at all. But are they taught this? No. They're taught 3 degrees every 15 minutes like everyone else, and that is because they will likely experience a drift of 3 degrees every 15 minutes like everyone else, because that's the tolerance for mechanical gyros with spinning rotors. So the remainder of the video talks about 2 different technologies that were employed back in the day to correct for drift in these gyro compasses. One of them seems perfectly logical and simple, and is probably still used today, to be honest. The other one is highly illogical, and I don't think it's used today. I've not seen any pictures through my research of what it looks like. It's called a latitude dial or a latitude compensation. But from what I've read into it, they never worked properly anyway. So that's kind of outside of the scope of this video, so I'm going to leave that for now. And I'm going to move on to some geometry and to show how much these gyroscopes should move at my location where I am presently. And I'm going to verify it using maths as well.
Okay, so exactly how far does the Earth rotate in 15 minutes? Well, we know it takes 360 degrees to do a full rotation, and we know it takes 24 hours, so let's divide that out. That gives us 15 degrees per hour, and we know there are 4 15 minutes in 1 hour, so let's divide that by 4, and that gives us 3.75 degrees of rotation every 15 minutes. So I've drawn the Earth here, and I've drawn a couple of gyroscopes, one at my location, just here, and one at the equator, just here. So if I just take a quick look, let's look at this one first from the side. You can see it's exactly perpendicular to the Earth, and just here you can see this one is also perpendicular to the Earth. If I switch to 2D wireframe mode, you'll see I've drawn a line up here at 53.06 degrees from the equator, which is my exact latitude, and obviously this one is dead on the equator. So let's switch back to 3D realistic mode, and let's pan around. Just take a look at it for a minute. Okay, so they are orientated like the directional gyroscope, like the one I have. And now we're going to rotate the Earth through 3.75 degrees. So you see it's rotating about the red axis there, and all I need to do is type in 3.75. There we go. So let's look at the one at my location first. Remember, I haven't rotated the gyroscopes. I left them in their original position since gyroscopes remain rigid in space. So now all I have to do is move the gyroscope into its original location without rotating it. Let's move it back to here. And I'm going to do the same with the one at the equator. So let's move it. And we'll take a look at this one first. We've got to reset the view so that we're looking directly from above again. And although the gyroscope has tilted over to the left at the top, it hasn't actually rotated clockwise or counterclockwise as viewed from above. It stayed in its original location. Let's look at what happens at my location. So I have to reset the view again, so we're looking directly above this location. Okay, there we go. And you can see it has rotated clockwise. So let's just put a quick angle on there to see by how much it is rotated. Three degrees. So it just so happens that my latitude corresponds to the exact correction degree that you're supposed to put into the gyroscopes every 15 minutes. But that is just purely coincidence. The further north you go, obviously the more the rotation occurs, and the further south you go, the less, until you get to the equator where there's no rotation. But anyhow, going back to my location, let's see if we can verify the 3 degrees that we've just witnessed here using maths. So let's get the calculator up again, and we know that the calculation is the sine of your latitude multiplied by 15 degrees per hour. So let's do that bit first. So it's 53.06, which is my latitude. We'll take the sine of that and times it by 15. That gives us 11.9 degrees of rotation per hour. And again, we'll divide by 4 to get the 15 minutes. 2.9972 degrees in 15 minutes. So it's 0.01 of a degree out. So hopefully you can see that the maths and the geometry work. We could do the geometry at the equator here, but since it's 0 degrees, the sine of 0 is nothing. So let's just, for the sake of argument, let's put 1 degree in so we can get an actual result. So I'll put 1 degree of latitude, take the sine of that, multiply it by 15, and we'll divide that by 4. That gives us 0.065 degrees of drift every 15 minutes. So obviously that's at 1 degree north of the equator. So if we was to say that was a 10-hour flight, that would be, we'll times it by 4 again to get back to the hour, and then times by 10. So there would be only 2.617 degrees of drift over a 10-hour flight, which is certainly different to what would occur at the pole. Let's just take the pole now, for instance, and we would put in, say, let's put in 89 degrees. Take the sine of that, times 15, and divide by 4. And that gives you 3.75 degrees of drift every 15 minutes at the pole. So, wildly different from 1 degree to 90 degrees. This would be very, very noticeable, in my opinion, on the directional gyroscopes, especially a flight that starts near the equator and flies either north or south.
Okay, I've put the directional gyro on my dashboard. I've stuck it with some self-adhesive sticky pads. Got the airline there, going to the compressor in the back here. Got a full tank of air. So I'm going to set this thing going, and I can't really set the compass heading correctly in here because I've got my compass here, but there are so many magnetic disturbances in this car. No matter where I move it, it changes. See there, I'll just move it slightly, it changes. So I can't get it in sort of a fixed position, but it doesn't matter. It's just the concept of the proof that the gyroscope actually works as it should do that I'm interested in. Now the gas or the air isn't going to last very long, but it obviously still spins once the air has gone for quite a long time. So really this is just to show that this gyroscope is behaving as it should do. I'm going to try and secure the camera as best I can. So normally we would take a magnetic compass reading at this point if it was in an aircraft, and we would use this cage dial and we would set in whatever heading we are currently facing. I know we're roughly about 270 degrees where I am here, so I'll put that in. I'm going to have a little short drive once I turn the air on and got the gyro spinning up. If you can hear it there. And let's go. Okay, so the compressor tank's empty now, but I can still hear it spinning, and as you'll see in a minute, it is still working as it should do. There you go, it's registering all the turns. Okay, I think you can see it's behaving as it should do. I'm going to turn around now. I'm going to pull into here and just stop, so we can just hear the gyroscope flywheel spinning. Turn the engine off a second. If you can hear that, it's still spinning. So it is working perfectly, and it will have experienced a little bit of drift there, which is to be expected. I think it's 3 degrees every 15 minutes is the sort of accepted tolerance. So let's see if we can keep it working as we go home. I can still hear it spinning.
Okay, this is where we first started, and you can see it has drifted very, very slightly. I know it's not under power at the minute, but it is expected to do that anyway. And we can hear it spinning still. We've still got the warranty warning stickers on. Okay, so I'm going to attempt to open this gyroscope up, have a look inside, see how it works. So I've got a selection of tools here. I hope it's going to be enough. You can see we've still got the warranty stickers on here, and they go across two pieces of what looks like black electrical tape here and here, going all the way around. I believe this electrical tape is used to stop air escaping from the joins here and here. When it's running, air seems to escape from this front edge here. That's where it feels like it's coming from. So it's obviously sealed around this back edge here. So I've taken the liberty of removing the 8 bolts from here already, and also the 5 bolts here. So I'm now going to cut this tape as best I can. Wow, that's quite complicated. So that's just fallen off. Seem to be these papery stickers here, but the gyro itself quite amazing. There's nothing electrical in here at all. No wiring of any kind. It's purely air driven. You see this gear at the bottom meshes with this gear and gives us the reading on the front. That's the cage knob. You can see it makes this gear mesh with this one, so we can set it manually, and that also disables this here. See, I can't move it now, whereas now it spins freely. I did notice something on the other side here. I say there's nothing electrical, but I'm not sure what this would be. It's a piece of wire, really, really thin, that's just touching on that wheel. Whether that's some sort of earth point, I'm not sure, but you would, if it was an earth, you would need to connect a wire to this, unless the case of it is actually earthed to the body of the instrument housing, which is in turn earthed to the body of the aircraft. But then again, aircrafts don't really have a proper earth, since they're not in contact with the ground. But it seems it is just as simple as that. This can't move all the way around. It's got stops just there and there. And then this is obviously free to spin round and round. So how does it get powered then? So I obviously had this bottom port connected for the air supply. So it looks like it goes down here. And it must go through this casing itself. And the air must be directed somehow at the flywheel. I'm guessing the flywheel must be inside, in here. You just can't see it. So the air must be directed to it. I'm guessing through these. One might be connected to the vacuum port, and one might be connected to the air inlet port. But they certainly go down into the bottom here. Yeah, I think that's how it works. The air goes in here, and then between these two pieces of metal here, there must be a chamber that connects somehow to the centre, which these pipes here are in contact with. So the air must come through here, up these pipes, and inside this thing, with the actual flywheel inside there. Can't actually see it. But I can't see anything more complicated than that. Hopefully I should be able to put it back together and get it working again. I'm going to take them out. Okay, so that's the teardown of the directional gyro, air powered. So we've now got the gyro on a stationary flat level surface, and it's connected to the air supply that goes outside. I've got a timer ready for 15 minutes, and I put a piece of tissue here so that you can see that the thing is constantly working and air is being expelled. It's coming out the side here. So I'm just going to quickly show you the compressor, and this might kick in again in a minute. It's really noisy, so apologise if it does. We've got it set to 1.3 bar. In fact, it's lost a little bit, so I'm going to turn that back up. Better. And that will just keep kicking in and out as it loses pressure. I'll try and close the door as best I can. Keep some of the noise out. So just to give it a bit of a demonstration. course cage it at the start of the duration test. So it's caged. I'm going to just cage it again for good measure. And let's start the clock. So what should actually be happening during this experiment is that this should be moving clockwise as viewed from above at a rate of 3 degrees every 15 minutes at my location, and this should also be leaning over like this. Obviously I've exaggerated it there, but that is what should be happening. Just a quick demo of it working. I've just spun it up and took the case off. And cage it again. If I apply a small amount of pressure onto this bottom gimbal, you can see it presetting there. So this cage knob resets it back parallel to the instrument itself. So it's important that we cage it before we do the test. So during straight and level flight, this whole setup here is not experiencing any friction on any of the bearings, only perhaps on the spin axis bearings of the spinning rotor itself, but that doesn't induce any mechanical drift. It's only the gimbal bearings that induce the mechanical drift. So in straight and level flight, nothing is moving, so no friction is being generated. If the pilot makes a maneuver that induces some sort of movement onto any of either this axis or this axis, it will result in a cumulative build-up of drift caused by all the friction. And this is exactly what the 3 degrees of drift every 15 minutes is for on every single gyroscope, no matter where it is on the Earth. So by not allowing it to move, i.e. testing it as we are doing on this flat level surface, we are not allowing any mechanical friction to induce onto any of these bearings. So if we eliminate mechanical friction or mechanical drift, all that should be left is apparent drift, which of course is what we're testing for right now.
So it seems to me like this would be the easiest experiment to perform in the classroom to demonstrate the spin of the Earth to children. The experiment's very simple. You set the gyroscopes spinning at the beginning of the class, and these gyroscopes could be easily mass produced in this day and age using electric motors. And you would give the student a map and get them to locate their current position on the map, find their latitude, then give them the sine formula to calculate the drift angle, get them to plot it on a graph over time, and this will obviously produce a sine wave. What better way to combine geometry, geography, maths, science, orbital mechanics, and obviously they will be able to check their result and check their calculations by reading off the angle on the gyroscope. But of course, nothing like this is ever done, and I think I'm beginning to see why. Unless, of course, I've got the only directional gyroscope in existence that doesn't register apparent drift. I mean, maybe I should donate it to a gyroscope manufacturer and get them to study it and see if they can replicate it as to why it's not showing apparent drift. If it's such a problem, then, you know, just study this one and replicate it. Problem solved. Anyways, I put a challenge out there a while ago for anybody to come up with a video demonstrating, with any correlation at all to their position on this earth, any apparent drift whatsoever. And as far as I know, nobody has come up with anything. We've had lots of people coming up with no movement on their gyroscopes, but nobody demonstrating anything that resembles movement in any shape or form. So the challenge still remains, and I'm not talking about ring laser gyros or anything of that ilk. I'm specifically talking about the types of gyroscopes that Leon Foucault and the US Navy claim show apparent drift. Anyways, I'm going to sign off now and leave you to watch the rest of the video. It goes on for 15 minutes, this experiment, but spoiler alert, it doesn't move. I hope you've enjoyed watching the video as much as I've enjoyed making it. I'll be back with another video hopefully soon. Cheers, folks.
Okay, that's 15 minutes up. Let's just show that it's still working as it should. $270. Back to 0. So 0 apparent drift at all.